Now let's talk a little bit about distinguishable permutations. Now here's the idea. Suppose that we have these 5 letters and we want to rearrange them in which, well, if we want to get the number of permutations, we care about the order. Which one goes first, which one goes second, which one goes third, all the way to fifth. So here for the first choice, we can see that we have 5 choices. So there's 5 letters to choose from for the first letter. And then for the second letter, now that we chose one for first, the second letter would be 4. So now we would have 4, and then for the third letter, we now have 3 choices. For the fourth letter, 2 choices, and for the fifth letter, we would have 1 choice. And the number of rearrangements of these 5 letters would be 5 factorial. But now, here's what we mean by distinguishable permutations. So let's get this word here, Peter. And here the order is going to matter. We can agree that this rearrangement and this rearrangement is different than this rearrangement. The word Peter, the word Epter, and the word Tapper are 3 different rearrangements. So these are 3 different permutations out of these 5 factorial that exist. However, here's what happens though. When we deal with letters, here we can technically rearrange the letters like this, where let's get this E, let's get that E, and we put this E right here, and we put this E right here. So you can see that even though I rearranged the letters, I still got the same word. I still got the same word of Peter. So now we don't have a distinguishable permutation. We actually have a repetition. So the goal here is to get rid of those repetitions. And we can do so by dividing by the rearrangements of all of the letters that are being repeated. So here we see that we have an E that's repeated twice. So we have 2 E's. And the way in which we can rearrange the E's is by 2 factorial. Hence, this 2 factorial represents the repetitions of, or the same version of this rearrangement. So that's what we're going to be dividing by. So 5 factorial over 2 factorial. And that's going to give me the total number of distinguishable permutations. So let's go ahead and generalize this process here. And to calculate this, the number of ways a group of n objects to be divided in subgroups where n1 are one type, n2 are a second type, n3 are a third type, etc. is by having n factorial and dividing it by each subgroup factorial. In our example, n objects was basically the group of letters that made the word Peter. And each subtype was each repeat. Well, in this example, we only had 1 letter that was being repeated, so we only had 1 subcategory. So let's try some examples. And I know the formula may look a little bit complicated, but I promise you that it's very easy to use. So let's go ahead and use it with this example right here, example 3. Find the number of distinguishable permutations of the letters in the word Hoover High. So we're going to count the number of letters. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 letters, so we know that we have 10 factorial rearrangements of these letters right there, Hoover High. And now we're going to divide by the repeats because we want distinguishable permutations. So let's count the letters that are being repeated, beginning with O here. So we can see that we have 2 O's, so we're going to have to divide by 2 factorial. That's because of the O's. And now we can see that here the H's are also getting repeated, and we have 3 of them. So we're going to have to divide by a 3 factorial, and that's coming from the H's. And those are the only letters that are getting repeated. So we're done here. 10 factorial has to be divided by 2 factorial over 3 factorial. So 2 factorial times 3 factorial. Again, the 2 factorial coming from the repetitions of O's, and the 3 factorial coming from the repetitions of H's. Now the last thing to do here is to simplify this. So let's go ahead and do it. So here, the 10 factorial, I'm going to expand it down to 3, since 3 is the biggest number on my denominator. So I have 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 factorial. And then I have 2 factorial times 3 factorial. The 3 factorials are going to cancel out. And now I have to calculate the numerator. And I get 604,800 getting divided by 2 factorial. But 2 factorial is just 2 times 1. So we get 604,800 over 2 times 1 is 2. And this is going to equal a total of 302,400. And that's the number of distinguishable permutations of the word Hoover High.